Welcome to science class. Today we're going to learn about metamorphic rocks. When we covered minerals, we discussed the 4 ways minerals form. Rocks are made from minerals, so the processes that produce minerals are the same processes that produce rocks. Crystallization from magma produces igneous rocks exclusively. Precipitation reactions produce sedimentary rocks exclusively. Heat, pressure, and hydrothermal solutions, the final processes, produce metamorphic rocks, also exclusively. Metamorphic rocks are the product of pre-existing rocks having their chemical composition altered. I said this many times before, but our goal in this course is to be able to learn about and interpret our planet. And metamorphic rocks, like anything else, allow us to do that, as long as you know what to look for. Let's get started. As I stated a moment ago, metamorphic rocks are produced when pre-existing rocks are subjected to either intense heat and pressure or hydrothermal solution. Metamorphic rocks can really only be produced several kilometers below the surface. For this reason, metamorphic rocks only make up around 12% of the surface. The temperatures required for metamorphism are typically greater than 200 degrees Celsius, and the pressures greater than 1,000 bars. How much pressure is that? It's almost exactly 1 ton per centimeter squared. Your pinky nail is pretty close to a square centimeter, so imagine 1 ton, 1,000 kilograms, over 2,200 pounds pushing on that. Yikes! But that's what conditions are like underneath that many kilometers of solid crust. Some of the temperatures that produce metamorphic rock are hot enough to normally melt rocks on the surface, but the massive amounts of pressure prevent the rock from actually melting. There are 3 basic types of metamorphism. The first is contact metamorphism. This occurs when rocks are altered by nearby magma. The degree of metamorphism is greater the closer to the source of magma. One rock may actually go through several stages of metamorphism. Shale, which you should remember is compressed mud, can become gneiss. But if the temperatures are not great enough or the amount of time not long enough, it may instead turn into slate, phyllite, or schist. Limestone is altered into marble at its lowest metamorphic state, but its mineral content can further rearrange to form calcite, chlorite, and serpentine at even higher temperatures, or garnets and diopside at even greater temperatures still. The next type of metamorphism is called regional metamorphism. Contact metamorphism was more about heat. Regional metamorphism is more about pressure. Rocks do strange things when they are subjected to the unbelievable pressures that we described earlier. I want to show you some sedimentary rock formations, and then compare that to metamorphic rock formations. See if you can spot the difference. Here's a sedimentary rock formation. Now here's a metamorphic rock formation. Sedimentary, metamorphic. Sedimentary, metamorphic. You see, when sediments are laid down, you always get horizontal layers of sediment. This is called original horizontality, and we'll go into depth with it when we cover historical geology. There's no way sediments can be laid down with these curves and undulations. This is the telltale sign of metamorphism. When you subject solid rock to the unthinkable pressures caused by 2 sections of the lithosphere crashing into one another, or by the sheer weight of 10, 20, 50, 100 kilometers of solid rock pushing down, those rocks start to do strange things. They can become altered as if they are clay. This is what regional metamorphism is. Already present minerals are also forced to recrystallize into new forms. A funny thing can happen during regional metamorphism. As the rock is squeezed, its mineral crystals not only can rearrange into new ones, but they can also realign so as to all face the same direction. Mica schist is schist that is high in the mineral mica. I know, right? Mica is actually a group of minerals. Muscovite belongs to this group, and we studied muscovite before. You'll remember it can be peeled into thin sheets. It is incredibly weak along one plane, but very strong along others. This is the result of regional metamorphism. All of the molecules have organized themselves that way, which causes these weak spots. When the minerals recrystallize along these planes, the rock sometimes exhibits these alternating bands. When the rock was a mixture of minerals pointing in random directions, there was no separating one from the other. but when they orientate in the same direction, stripes of one mineral are distinct from others. This is called foliation, and it's how metamorphic rocks are classified. Foliated metamorphic rocks have this distinctive banded appearance, while non-foliated metamorphic rocks do not. Gneiss, phyllite, and mica schist are examples of foliated metamorphic rock. Marble and quartzite are examples of non-foliated metamorphic rock. The third way of producing metamorphic rocks is through hydrothermal solutions. This is exactly the same as the process we outlined when we covered how minerals are produced. But again, superheated water, which carries with it minerals or metals that are in solution, permeates through the cracks in the rock or the porous nature of the rocks themselves and cements new minerals within the rock. This is not as extreme as heat and pressure, but it does alter the mineral composition, so it counts as metamorphism. So we have used igneous and sedimentary rocks to interpret Earth's history in different ways, and we can do the same with metamorphic rocks. Metamorphic rocks are pretty distinct. The warping that is plainly visible on their surface is one giveaway. Mount Rushmore is carved into a granite peak, but its base is actually metamorphic rock. You can see what's known as an unconformity between these two layers of completely different rock. We know what the conditions are that produce different minerals. When we find gemstones and minerals and whatever else on the surface that we know could not have been produced without the insane heat and pressure of metamorphism, we know that those particular minerals or rocks originally formed deep within the earth and very slowly were brought towards the surface. Now I want to tell you a story about a little coral reef. This will make more sense shortly. This coral reef lived probably hundreds of millions of years ago and existed for probably tens or maybe hundreds of thousands of years. Corals take in nutrients from the water and then cement the minerals into the shallow sea floor. That's what the bulk of a reef is. The animals themselves are called polyps and are very, very small, and there are thousands of them. Reefs never stop growing, and they eventually build on top of the structure built by corals from many generations ago. After a very long time, the mineral buildup from this coral and many microscopic organisms became buried and compacted. This is what forms limestone. The shifting lithosphere later buried the limestone deeper into the lithosphere, where cooling igneous rocks transformed that limestone into marble. After more eons still, the marble was exposed to the surface in Carrara, Italy. Quarry workers extracted a section of the marble, and an artist named Michelangelo transformed this block of the earth, hundreds of millions of years in the making, into the statue of David, one of the most iconic works of art ever produced. Did those events unfold exactly that way? Yeah, probably not. But that is one of the ways in which rocks transform on our planet. We call this the rock cycle. Any rock can be melted and crystallized into igneous rocks. Any rock can be weathered and compacted and cemented into sedimentary rocks. And any rock can be transformed through metamorphic processes. We've covered how rocks and minerals form and how life, which provided the free oxygen to react with minerals and rocks to form brand new minerals, transformed the geosphere of Earth. So we don't really need to get into heavy details with the rock cycle. Just know that any rock can transform into any of the other three types of rocks. But here's a good question. What was Earth's first rock? If you remember planetary formation, you'll remember that Earth was molten all the way up to its surface during and after its formation. So the first rock had to be igneous rock. But which one? Well, since it formed on the surface, it had to have been an extrusive igneous rock. And since it was crystallized from lava, it was almost certainly basalt. The entire surface of Earth, when it first stabilized, was 100% basalt. How did it ever transform into other rocks? Keep in mind that rocks just don't sit there in place, not reacting with other parts of Earth. Plate tectonics, liquid water, and a just barely chemically diverse enough atmosphere drive the minerals in rocks to form new mineral compounds. As basalt is driven deeper into the Earth, weaker minerals melt and rise. These weaker minerals form new rocks, especially granite. Metamorphism can happen at any point from heat and pressure, and sedimentary rocks could start forming once these materials began to be broken down by water and ice. That does it for rocks, but next time we will begin learning about a different set of resources on our planet: energy resources. Thanks for watching.